Okay, wonderful. Let's get started. First of all, thank you all again for coming out. It's so lovely to see so many of you here, giving up your Wednesday night to learn all about science. So we've got some good news for you. We are going to make the best of it with stargazing and actually try to do it. I know we told some of you no. The clouds are looking very tentative, and we thought it's just been such a bad season, we'd be silly not to try. So we're setting up telescopes outside. So whatever happens, we're going to be done with the talk. We will leave you onto the lawn for some stargazing. It might be that we only get to do it for 15 minutes and the clouds will roll in, but at least you will have seen something, right? So the plan for the evening is talk followed by stargazing. So we're very lucky to have Professor Pascal Hirsch visiting from the University of Geneva. He is our colloquium speaker tomorrow. He's an expert in all things James Webb and the early universe. And he very kindly volunteered to sort of share his expertise and give us a public version of tomorrow's lecture.
Thank you.
So,
Thank you. Well, hello everyone, and thank you very much for being here in such a big crowd. Sorry for my voice. I was visiting the department already today and chatting to too many people. So anyway. So today we're going to take a journey across cosmic time and space to the very beginning of the universe together, and as far as we can see, essentially. And so we're doing this with the James Webb Space Telescope. And so, but before we start, I want to, let's start a bit closer, right? This is an image I found on Sky at Night magazine, taken in Dorset. And of course, what you can see here is the Milky Way. Maybe this doesn't work. Anyway, you can see the Milky Way galaxy that is peeking out from here, the ocean. And essentially, the Milky Way, right, is our galaxy. That's a disk that we're seeing here from Earth. And so if we could look at the Milky Way from outside, what we would see is that it's a disk galaxy, a spiral galaxy. It has these spiral arms. It has a bulge in the middle. And essentially, it has about 100 to 400 billion stars. They're sitting in this disk, a diameter of about 120,000 light years, and we're sitting about halfway from the edge of the Milky Way to the center, essentially. And then the other thing to keep in mind is that galaxies, they grow by essentially converting gas that is available in the universe into stars. So they're forming stars, and you can see that in these little pinkish regions. That's where the Milky Way is forming stars, and essentially it's forming stars at the rate of about one new star per year, one sun per year, essentially. So now this is our galaxy. This is what we can study from around us. But if you're looking around in the universe, essentially what we're seeing in our kind of local neighborhood, that there's a huge diversity of galaxies. There's lots of these disk galaxies like our Milky Way, but the more massive galaxies actually are more in this kind of elliptical shape. You can see them, they're kind of roundish, orange in color also. And then lower mass galaxies are much more these bluish kind of galaxies that are forming stars at a much higher rate than our Milky Way. And so essentially, the big question that we have is, where do all these galaxies come from? Where did this all start? And so before we jump into James Webb, we're talking about the Hubble Space Telescope, because Hubble has really opened up our view of the very early universe. It was launched about more than 30 years, has been in space, and has been observing all this time for us. And so with Hubble, it's orbiting around Earth. We observed a tiny little part of the sky. You can see this here in comparison to the moon. This tiny little part we've observed for essentially a full month. We're exposed in this one little patch of sky with different filters, different wavelengths, essentially. And so we call this the Hubble Ultra Deep Field. And what we have found is essentially that the universe is really completely full of galaxies. Thousands of galaxies in this tiny, tiny little patch of sky. And essentially every single colored dot that you can see here is a galaxy, except for a few these stars that you can see here with these crosses. Those are stars in the Milky Way, but everything else are really galaxies in the very early universe. And so Hubble has shown us the universe is full of galaxies. And then beyond that, the interesting thing is now in astronomy, we can actually look back in time, because the speed of light is finite, and so we can slice up this image essentially and look billions of years into the past. And so that's exactly what is shown here. We essentially can measure from the colors, we can kind of identify the distances to these galaxies, and we can see that these first few galaxies are less than 5 billion years apart from us, 5 to 9 billion years in the past, and then more than 9 billion years. So this light took 9 billion years to reach us, to reach our telescope. And so essentially what we're doing here in observations is like slicing this galaxy population up and kind of trying to piece together how did the galaxy population form and evolve over these 13 billion years of cosmic history. And so what we can see here, of course we cannot follow an individual galaxy, so we have to do this statistically, but we can still see how galaxies were as we're going further back in time. And you can kind of see this as an idea here as a kind of a flick book of galaxies over time. When we're looking at a spiral galaxy in the more local universe, like our Milky Way, as we go further and further back in time, we can see that there's still some spiral structure, but as you go, beyond halfway, let's say, of cosmic history, essentially these morphologies disappear. We don't have spirals anymore. There's all these very clumpy structures. So galaxies are much more clumpy in the early universe. And as you go really far back, essentially they're just little dots. So really baby galaxies. And so the idea is, how did this galaxy population evolve across cosmic history? And so what we really want is like, when did this first start, right? When did the first galaxy start? And so to do this, we will do a little bit of early cosmic history together. So the universe started with a Big Bang. I assume you've heard about that. There's a whole TV show out there, right? The Big Bang Theory. And then the first most distant light that we can actually observe is the cosmic microwave background. So that's this image that we can take. This is a full sky image, essentially. This is a signal of 400,000 years after the Big Bang, after the beginning of the universe. And so what we can see here is all these little nice colors, or these tiny density fluctuations in the distribution of matter, and that will become important later on. And so this is the most distant signal that we can observe. And then after that, the universe was essentially completely dark. There were no sources of light. There were no stars. There were no galaxies, nothing. And so we actually call this the cosmic dark ages. And so essentially these tiny little density fluctuations that we've seen just in the image before, they started through gravity. They started to grow and grow further. Gas started to collapse into these fluctuations, and at some point the first star started to form out of this gas. And then another, and another. We don't know exactly when this happened. We cannot observe this directly, but we think from theoretical models that this was maybe between 100 to 200 million years after the Big Bang. And then the first galaxies after that formed, after this. And so let's recap. So the first most distant light that we can see is 400,000 years after the Big Bang, cosmic microwave background. Then we had these dark ages. First formation of the first stars, 100, 200 million years after the Big Bang. And then we're really forming the first galaxies, maybe 200 to 300 million years after the Big Bang. Again, this is what we're currently studying. And then later on, the rest of the galaxy population and this large diversity of galaxies that we see in the universe around us today start to form. And so our observational frontier is essentially this part here, this 200 to 300 million years after the Big Bang to the first 1 billion years, essentially. And so the idea is that we want to understand all the physical ingredients that formed and are important for galaxy formation. You can do this from a simulation side, for instance. So this is a simulation that shows how these little matter over densities started to grow through gravity. In the centers of these fluctuations, you start to form galaxies. Gas is starting to cool, starting to form stars. Stars is they're heating up the universe and so on. And so this is the simulation part, and what we are trying to do from the observational side is really trying to understand, to find the real galaxies in the real universe and then compare these to the simulations. And so in this way, we kind of really try to understand how galaxies form across cosmic history. So the step number one is we need to identify these galaxies. How do we do that? And so essentially, we can make use of the fact that in the early universe, there's still a lot of neutral hydrogen in the universe. Neutral hydrogen, that's just a proton and an electron around it. And so if you have a distant galaxy, it's, as I said, it was forming stars very rapidly. With these, if galaxies that are forming stars rapidly, they're very blue, they have young stars, they're very hot, they're shining bright in the ultraviolet light. Now, if the photon, if light from these early galaxies starts to hit neutral hydrogen atom, which is indicated by these blue clouds here, if the photon is energetic enough, it can ionize this hydrogen atom. So it separates the proton and the electron from the proton, but this light will be absorbed. And so that means that essentially this galaxy now will missing the blue part of the light, the red part can still go through, and so this galaxy will appear red to us. So there's this kind of absorption of this light from the neutral part, the neutral hydrogen in the universe. And then this light actually gets stretched to longer wavelength. And so we call this redshift. This is because the universe is actually expanding. And you can really think of this expansion of the universe like a balloon that is blowing up. The universe is getting larger and larger. Galaxies are moving away from each other. And essentially you have this light that is traveling across the universe is really stretched to longer and longer wavelengths. And so that's what we call the redshift. And essentially it's what we really measure for these distant galaxies. The main point is that the light is stretched to longer and longer wavelengths, and you can kind of see this extension of the light. And then on the y-axis here, I have time in the past. So the further we want to look back in the past, the more the light is stretched. And unfortunately, this is not a very linear relation. You can see it's actually very non-linear. So if you want to go halfway across cosmic history, the light is stretched by a factor of 2 to longer wavelengths. But if you want to go and observe the most distant galaxies, essentially 500 million years after the Big Bang, at that point the light is stretched by a factor of 10, and it gets stretched much, much faster the further back we want to go. And so that's essentially why we cannot use the Hubble Space Telescope to observe these very distant galaxies. That's why we need a new telescope, James Webb. That's exactly shown here, because we need these near-infrared wavelengths. So these very distant galaxies are completely invisible to Hubble because all the light was absorbed and then stretched. So we need James Webb. And so James Webb is observing now at longer wavelengths in the near-infrared that we can actually observe these galaxies. And so the telescope, right, is much bigger than the Hubble Space Telescope as well. So we have now a 6.5 meter a mirror here that's gold-plated, so the light arrives here, bounces off there, and then goes to the other side. You have here this, in the middle, you have kind of like a tennis court-sized shield, essentially, that is shielding the light from the sun. So the sun would be on this side here. The telescope, the mirror itself has to be kept extremely cool because we're observing in the infrared, and so if the telescope is warm, it will emit light there as well. And so yes, so the telescope was then launched almost exactly 4 years ago on Christmas with an Ariane rocket, and it was really launched perfectly into orbit. You can see this was the last image we have of the telescope in orbit. And what you can notice here is that this telescope doesn't look like the telescope I was showing you before, because it was all packed up. It had to fit up in this in the top part of the rocket. And essentially, as the telescope then was traveling to its final orbit, so it's 1.5 million kilometers away from us, it was starting to unfold, and all completely autonomously. So there were essentially 400 points of failure. Essentially, if they didn't work, the telescope would not be observing today. But everything worked. But it was 6 months essentially of excitement, or well, we had to wait for 6 months until the telescope really was taking its first images. So yeah, fully unfolded and after 6 months, we finally started to observe. So this is a field, the first image of James Webb. This is not James Webb, but this is with the Spitzer Space Telescope. I had previously observed this one field, so this is now at similar wavelength as JWST, and then with James Webb, now we can finally see the same exact field, And you can see the enormous improvement just because the telescope is much bigger, but also it can observe at these infrared wavelengths. We have 100 times better sensitivity, also spatial resolution, obviously, and we can really see the universe finally, like you put on your glasses, and you can finally see the universe in its true form. And so it's really been amazing. And so immediately in these images, we could start to look for these extremely distant galaxies that we could never see before with the Hubble Space Telescope. And that's exactly what happened. Essentially, we looked at these first images, and this is just the big field of all the galaxies at all the distances. But there's this one little spot here in the middle, and if we zoom in, this is what we saw. So this is a source. We can measure its distance again from the colors. And identified this to be at redshift 12, so the light of this source was stretched essentially by a factor of 13, and really is a galaxy that we would have never been able to see with the Hubble Space Telescope, so beyond what Hubble would have been able to see. And so we immediately found this one source in the first images essentially of JWST, and it was extremely surprising. There was a second one, again, slightly closer to us, but both of these about 400 million years after the Big Bang. And you can see that they were extremely bright, essentially, and really extremely surprising for our models. We expected that we'd take 1 full year of observations with the James Webb Space Telescope to find 2 such sources. And here we are in the first images, essentially already finding 2 of these. We could also measure how many stars these sources are forming and how many stars they had. And essentially it turns out they already had 1 billion, so 1 billion solar masses in stars. So only about 100 times lower than the Milky Way. So again, extremely massive already for 13.4 billion years in the past. And so it was really a big surprise. And the models that really didn't expect these, and so we had to really start to work on our models essentially to be able to figure out what's going on. And actually, we could even probe further back in time now. Now we have very deep imaging. This is the JADE survey. This is actually also co-led here from Cambridge. Found galaxies at all kinds of distances, essentially up to 300 million years after the Big Bang. So we now finally know that galaxies definitely had formed 300 million years already after the Big Bang. Some of these have only like 10 million solar masses, so solar suns essentially, but nevertheless already in this, when the universe is only 2% of its size, of its age, we already had galaxies there. And so this, again, was something completely unexpected, and the models really had to catch up to reproduce these galaxies. So then the next thing with JWST, we can not only measure the light of these sources with imaging, but we can actually also, for the first time, take spectroscopy. So that means we can break up the light essentially into its different components, like in a rainbow. And so that's shown up here. So this is a source that was highlighted 13.1 billion years in the past. And you can see up there the spectrum, again, the light split up in its different components, different wavelengths. And from this, what we learn, essentially, we can measure the distance to the source perfectly. But then we can also measure the temperatures, the densities, the chemical composition. You can see all these different elements that are highlighted. And again, it's the very first time that we could actually do this. We've never been able to measure these kind of things at these extreme distances. And the most important thing is, again, to measure the distances from the stretching of the light, essentially. And so the most distant galaxy that we have confirmed so far, this was in one of our surveys. We call this mirage or miracle, because in the very early times, again, we found these extremely bright sources, and we didn't know, are they actually at these distances? Just from imaging, you could have some, you can make some mistakes. And so we were not sure if these were mirages or actually miracles that really needed our models to completely change. And so it turns out some of these were miracles, and this is one of them. Again, you can see the spectrum doesn't look super impressive. But you see this kind of break there. That's again because this neutral hydrogen is absorbing the light. And that's how we measure the distance to this galaxy. And then, yeah, it's extremely small. This now here has only 100 million suns, essentially. And it's also extremely compact, as you can see. But this is the most distant source that we have currently found. And, yeah, hopefully we'll find more in the future. But it's clear now, as you could see, that JWST is really rewriting the early cosmic history. Before JWST was launched with the Hubble Space Telescope, we have been able to push into this realm of the sort of first galaxies. We had confirmed the distances to some of these up to about 400 million years or so after the Big Bang. But now with JWST, we can really push much further and really have also spectroscopically confirmed galaxies that we know that are actually at these distances when the universe is only 2% of its current age. And so we really don't know exactly the most distant galaxies. We haven't found them yet. But we're working on this, and so there's really many exciting scientific results that are still coming over the next few years. And so, yeah, thank you very much.
Wonderful. Do we have any questions for our speaker? I'm going to limit it to just a quick couple of questions because there's a risk of clouds, and we want to sort of have good talks and stargazing. So we'll do first one there, please. Sorry, the girl behind you.
Oh, that's a very good question. We don't know. Easy answer. Sorry.
Okay, and then
How do you know how many solar masses are in those 12 galaxies?
How we measure the mass, essentially? Yes. So essentially we are comparing to a set of stellar spectra, and then the normalization tells us how bright these galaxies are, essentially tells us roughly what's the stellar mass. So we're taking spectra of stars, we're putting them together as a stellar population, and then the normalization of that tells us roughly how bright, how massive how many stars there are. Yeah. There's some assumptions. Sorry, yeah.
It's multi-directional, right?
Yeah.
The telescope.
Yes.
So you can't put it towards the sun,
No.
obviously. So are there any parts of the sky that it can't?
No, we can observe the telescope, as we move around the sun, the telescope moves essentially in the same way, and so we can observe everything all the time. I mean, we can, at some point in the time, twice per year essentially, we can observe every point, but there are some points that we can observe all the time, up and down. Yeah.
Yes, in the back, please.
In the future, how far do you think will we be able to see that close to the Big Bang?
Yeah, that's a very good question. That's what we're trying to do. We're trying to push our observational frontier further and further back. I think we're close. We're close to how much we can do, but we're trying to observe deeper. So essentially, as we go further back in time, the galaxies become smaller and smaller. So it's more and more difficult to detect them. So we need, in principle, bigger telescopes than JWST, which we won't have, I guess, for the foreseeable future. But I think we're very close to the first galaxies, but we haven't found them quite yet. So just a little bit further, I think.
Okay, should we do one more right to the front?
Because obviously the light source comes to the James Webb Telescope, but if they're trying to go back to the Big Bang,
Mm-hmm.
would there be any light source to actually come back? So then, if there isn't, then how would they be able to go back that far?
No, I mean we can only see light. We can only see stars. If the stars are shining, we can potentially detect them. But at some point there won't be any stars anymore, and so yeah. So that's the limit. How far we can watch, how far we can see essentially. Technically, the telescope could see much further back in time than what we have seen at the moment. So technically, that's all possible. It's just the sources are not bright enough, essentially, at the moment.
Okay, I'm afraid that's all we've got time
Okay.
for. If only because we do want to be able to observe something. So first of all, thank you. So quick housekeeping note. You can follow us out to the lawn. There will be a floor show in front of you. There'll be telescope domes to go in. There'll be a telescope with a red rope light leading through it. Don't neglect that one. We will observe as long as we can until the clouds roll in. The way the crowd are going to go up the steps.
Thank you.
Can I ask
Hi.
you a question?
Sure, yeah.
How do we choose and who choose where we point the telescope?
That's a very good question. So it's